when we query multiple tables, then we usually need join conditions. They specify what combinations of the rows we want to consider. So for example, imagine that we want to have all the results of a particular student. Then we query the student and the results table, but we need some condition that links the results to the student. So that says that we only want to consider those rows of result that match the current student that we are looking at. So here we have an abstract query that queries the table students and results. The tuple variable s iterates over the rows of the students table. The tuple variable r iterates over the rows in the results table. In the students table we have 5 rows. In the results table we have 8 rows. So in principle all possible combinations will be considered. So this is 5 times 8, 40 combinations. Conceptually you can think about this query as being executed like this nested for loop. The outer loop iterates over all the rows in the students table. The inner loop iterates over all the rows in the results table. Then we check whether the condition C in the where clause is true, and if so, we print all the attributes that are selected in the select clause. Of course, a good database management system will choose a better strategy for evaluating such queries. And this is the task of the query optimizer. The query optimizer looks at the query, in particular the condition C in the where clause, and tries to determine the best strategy, the most efficient strategy of evaluating this query. So in particular, imagine that the where clause contains the condition s.sit is equal to r.sit. A database management system usually builds index structures for efficient access over key attributes. The sit is a key attribute for the students table. So given a sit, we can use, or the database management system can use these index structures to efficiently retrieve the student with a particular sit. So one possible strategy for the database management system could be to loop over the results table and to use the index structures to efficiently look up the matching student. So then there's no need for having these 2 nested for loops. We just need one for loop and this efficient lookup procedure. Now, while this query optimizer may choose any other strategy to evaluate the query, the main important thing is, for understanding the semantics of the query, we do not need to understand how the query optimizer works. For understanding the semantics of the query, the simple nested for loop that we've seen on the last slide is sufficient. The query optimizer can choose any other strategy, but the output of the query optimizer, the result of the query, must be the same as the simple for loop that we've seen on the last slide. So let's say we want to have all the results obtained by student George Orwell. So we query the students table, we query the results table, and in the where clause we specify a condition for the rows in the students table that we want to look at. Namely, we say that we only want to look at those rows where the first name is George and the last name is Orwell. And finally, we say that in the output, we want to have the category, the number, and the points of the results. So let's execute this query. This looks a bit much. So let's look up what student George Orwell is. George Orwell is the student with number 101. And if we look at the results table, then we should have 3 results of George Orwell. But this is much more than 3 results. So what goes wrong? It becomes more clear what goes wrong if we include also the sit of the results table in the output of this query. And then we see that actually we get all the results of all the students. And the problem is that although we have specified that we only want to look at the student George Orwell in the students table, we haven't restricted at all at what results in the results table we want to look at. So we need to have what is called a join condition that specifies that we only want to look at those rows in the results table where the student ID matches the student ID of the row in the students table that we are currently looking at. If we add this join condition, namely that the row in the results table has to match the SID of the row in the students table, and we only look at the student George Orwell in the students table, then we get only those results of George Orwell. This slide shows the query that we've just constructed, and here we have the join condition that correlates the rows of the students table with the rows of the results table that we want to look at. Now let's look at one more example. Here we also query the students table and the results table, and in the where clause we say that we only want to look at those rows where the category is homework and the number is 1. So category and number are attributes of the results table, so we only look at those rows in results where we have the categories homework and the number is 1. So that is this row, and this row. So we look at 3 different rows in the results table. Now let's have a look what's the outcome of this query. So we paste the query in the query testbed and we execute the query. And now we see that we have a list of all of the students in our students table, and each student is listed 3 times. Now why is that? The reason is that, again, we have a missing join condition. So we look at the students, but there is no condition that actually restricts the students which we are interested in. So we're looking at each of the students and we're doing so 3 times for every row in the results table that matches the criterion in the where clause. And we've just seen that there's 3 different rows in the results table that fulfill this condition. So that's why every student is listed 3 times. Now again, we have to correlate the rows in the results table with the rows in the students table. And of course we do so by saying that we want to only look at those rows in the students table where the SID of the student is equal to the SID of the row in the results table. Now we get the result that George Orwell has submitted homework 1, Elvis Presley has submitted homework 1, and Lisa Simpson has submitted homework 1. As a general rule of thumb, one can say that it's almost always a mistake if you have 2 tuple variables that are not linked via join condition, and this link is allowed to be direct or indirect. Let's have a look at an example. Here we query 3 tables, the students table, the results table, and the exercises table, with tuple variables s, r, and e respectively. The first condition in the where clause is a join condition for s and r. It specifies that the SID of s needs to be equal to the SID of r. Next, we have a condition that joins r and e. It says that the category of r needs to be equal to the category of e, and the number of r needs to be equal to the number of e. We can display these join conditions in a so-called connection graph. Here we see that s and r are connected via this join condition, and r and e are connected via this join condition. So indirectly, also s is connected with e. All of the tuple variables in this query are connected. And what you see here is that these join conditions usually correspond to the foreign key relationships. So SID is a foreign key in the results table referencing the students table. So this join condition says that the SID of R has to match the SID of the student. Likewise here, this is also a join condition corresponding to a foreign key relationship. The category and the number together are a foreign key referencing the exercises table. And this join condition exactly expresses that the category and number of the result has to match the key of the exercises tuple. And this is not an accident, this is the usual scheme it's very common that these join conditions for these tables will correspond to precisely these foreign key relationships. So let's say we want to formulate the following query. We want to have all the topics of the exercises solved by George Orwell. So it's clear that we need to query the students table. We want to find George Orwell. We need to query the exercises table because we want to have the topic of the exercise. So we start with a query approximately of the following shape. We say that we query the students and the exercises table. We restrict the attention to the student George Orwell. And we say from the exercises, we want to have the topic in the output. But we are not done yet, because S and E are not yet connected. So at the moment, we are not only looking at the exercises of George Orwell, but at arbitrary exercises. So how do we solve this? It often helps to look at this connection graph. Here we see that the students table is linked with the exercises table only indirectly, via the results. So in this connection graph, we have only one possible path. We need to establish the connection via the results table. So we also need to query the results. And how will we then establish the connection between students and results? Via the foreign key relationship. So the set of the results has to match the set of the student. And the relation between the results and the exercise, we also establish via the foreign key relationship. We make sure that the category and the number of the result matches the category and number of the exercise. So this brings us to this query, where we now have two join conditions. We link R and S by enforcing that the set has to match, and we link R and E by enforcing that category and number have to match. And R is of course this extra table results that we have to include in our query in order to establish the link. So the connection graph with the foreign key relations may help us to find out how to link certain tuple variables. However, in general, the connection graph can contain cycles, and this makes the selection of the right path more difficult. For instance, in this example, we have a database with course enrollments. So we have students and we have courses, and we have enrollments which link the students with the courses. But we also have teaching assistants in this database that also establish a connection between the students and the courses. So in the presence of cycles, we really have to think about which path it is that we want to choose. And this of course depends on what output you want from your query. When deciding what tables to query and how to join them, you should in general not query more tables than necessary. Usually the query optimizer eliminates redundancies, but there is a risk that the query optimizer overlooks the redundancy, and then when querying additional tables, your query can be significantly slower. Let's have a look at an example. Here we query the results and the exercises table. In the where clause we say that we only look at those exercises where the category and the number is homework 1. And we have a join condition saying that the category and number of the result has to match the category and number of the exercise. In the output we only include attributes of result. We include the set from the results and the points that were obtained. Now, the question is, can we eliminate this table exercises? So is this query equivalent to the following query, where we only query the table results, and we say we want those results for homework 1. Now if we look at the yellow query, the first thing we observe is that here we can write r.category instead of e.category. And here we can write r.number instead of e.number. Because r.category anyway is equal to e.category because of this equality, and r.number is equal to e.number because of this equality. So we can exchange this e's by r, and then this condition already looks a bit like this. Now, can we eliminate this table exercises from the from clause and this join condition from the where clause? So what is the condition that has to be satisfied that we can eliminate this? It does not change the result, the output of the query, if we know that for every row in the results table that's included in the output, we have precisely one matching row in the exercises table. So put differently, the risk is if we eliminate this table, then we eliminate the join condition. If there would be no row in the exercises table that fulfills the join condition, then this row would also not be included in the output. So then we would have a result missing, and then eliminating this table would include one more result in the output. However, we have this join condition corresponds to the foreign key relationship. So we know that for whatever result we look at, so whatever r.category and r.number is, there's precisely one matching tuple in the exercises table, because the category number is a key for the exercises table. So for every row in results, we have precisely one matching row in E, so that means we can eliminate this query about the table E without changing the result. So these two queries indeed will give the same result. So what will be the result of this query? Here we query the results and the exercises. We include in the output the student ID of the results and the points, and we restrict to those results for homework 1. Now, what is missing here is a join condition that links R and E. So let's have a look what this. So let's paste this query in our query test pad and execute it. So we see that we have 10 points for student 101, 9 for 102, 5 for 103, and then it repeats 10 points for 101, and in total it repeats 3 times. So why is that? Of course, the problem is again that we have no join condition between R and E. So we look at all the results for homework 1, but we do so for every row in the exercises table. And the exercises table happens to have 3 rows. So if we eliminate this table, we get the query that we've seen on the last slide, and this gives us exactly the points that were obtained by the students for homework 1 without duplication. Let's consider the following 2 queries and let's discuss whether there's a difference between the 2. The first query queries the students table and selects the first and the last name. So basically we will get the students table where the columns sit and address have been dropped. So we only keep the columns first and last. The second query queries the students and the results table, and we have a join condition that says we only look at those rows from the students and the results table where the sit from the student matches the sit of the result. So in other words, we look only at the results that belong to the student that we're currently looking at. Again in this query we select the first and the last name of the student in output, and we have this extra keyword distinct here. The distinct says if the output contains duplicate rows, then the duplicates are removed. So every row appears only once in the output. So for the moment, let's assume there's no keyword distinct. So let's ignore the distinct. Then what's the difference between these queries without the distinct? In the second query, let's say that we have S is assigned to student George Orwell. S iterates over the rows in the students table, so at some point it will be assigned to student George Orwell. So now S points to this row in the students table, so the sit is 101. So that means we are looking at the result rows because of this join condition. We are looking at this result row, and this result row, all belonging to George Orwell. And for each of these results, the join condition is true, so George Orwell will be included 3 times in the output. So a student is included in the output as often as the student appears in the results table. Bart Simpson does not at all appear in the results table. So when S is assigned Bart Simpson, then there is no result row that matches the SID 104. There is no result for SID 104. So Bart Simpson will not be at all in the output. So in the first query, every student, every name, first and last name, appears as often as we have a student with this first and last name. So we could have 2 students with the same first and last name, then they would appear twice. In the second query, every student, or every first and last name, without a distinct, appears as often as these students with this first and last name have homework results. So a student that has no homework result will not appear at all in the second query. Moreover, if we include the distinct, then we remove the duplicate rows, then what we get in the second query is the first and last name of all the students that have at least submitted 1 result. So that have 1 result in the results table. However, if there's 2 students with the same first and last name that have results in the results table, they will appear only once due to the distinct. The distinct will remove the duplicate rows. Whereas in the first table, if we have 2 students with the same first and last name, they will appear twice.